Hi everyone, this is Dr. S. Kannappan presenting the course Computer Architecture and Organization. It is very crucial the computers architectures in many applications. We know the computer architecture is evolving from the basic processor architecture to multiprocessor architectures, and the organization of the processor and all the components of the computer makes a huge difference the computer various processor computer architecture. So in this course we'll cover the basic operation that takes place in the processor to perform any instruction. The instruction level operations performed in the processor will be covered, and how the processor is interconnected with other modules, other components of the computer to perform any operation. In this module, the module 1 covers the micro operations in the processor, and then the micro operations performed at the register level. Hence, it is called register transfer language and micro operations. Just so before going to discuss about this register transfer language, let us consider the basic concept behind microprocessor or any processor. The processor will work on the concept called stored program execution. To perform any application or to use any application in the computer, the application program has to be stored in the memory, and the processor has to execute the program instruction by instruction to perform the task that is required for the fulfilling the application. So this complete process of execution will be taken place within the processor architecture, and the programs are fetched from the memory instruction by instruction, and it is executing using the resources available within the processor. The basic important resource to hold the instructions and the values that are to be executed will also be stored in the registers. So the basic level instruction in the processor, or the basic instruction that is to be executed in the processor, is micro operation, and that micro operations are performed within the register level. And suppose the instructions that are used to display the values on the monitor, or it wants to send the data to the USB drive, or it wants to store the value into the memory. It is some complicated operations or some bigger operations contains combination of multiple such micro operations. So the small instruction is executed with the help of these small internal micro operations. As a whole, just we can see one instruction is executed means it is internally done by multiple register transfers. So we'll start the execution of the instruction from the bottom level. So how internally these basic instructions will be executed. So that's why we'll start from the root level, that is register transfer level, and what are all the micro operations that can be performed within the processor. And then we'll go to the higher level. So to complete a program, how the instructions will be uh, correlated or interconnected. The values stored in the first instruction will be passed to the next instruction, and how this is organized, that will go for the instruction level for the next in the next module. And then further we'll go for interfacing with the input devices and memory devices in the further coming modules. Such a way we'll focus on learning this micro architecture of the computer, and then how it is organized to perform any application with the help of execution of instructions that is specified in the stored program. So this module 1 covers the following topics: register transfer language, what is register transfer language, how it is specified, and what is meant by register transfer, and from register internally to register transfer to when we want to fetch the instructions from the memory, we have to go for memory transfer, and it is not directly coming from memory to register, it has to come via bus. So that's why there is a two transfer apart from register transfer, that is bus and memory transfers. And next one is, and after transferring the data from the memory to processor, processor has to do some operations. So these are all the basic operations that we can see in any processor. There's arithmetic operations, logical operations, and shift operations. But the arithmetic operations may need some internal basic operations. The basic micro operations are going to be discussed here. Arithmetic micro operations and logical micro operations, shift micro operations. So simply arithmetic operations may be any complicated operation, but arithmetic micro operation is a very basic arithmetic operation that is to be done in just register level of operations. And logic micro operations, shift micro operations are also as like arithmetic, but the operation is logical, but it is done in the registers only, and shifting the registers and different kinds of shifts. And combinedly, all these micro operations placed in one module to perform any operations among these three, based on the instruction, it will automatically enable these three modules, and then it will complete the task. And this will be collaborated with the control unit to perform which operation has to be processed. Now, let us see what is micro operation. So, micro operations is nothing but the instructions or operations that are performed within the register level. So, that is called micro operation. The functions built into the registers, for example, simple shifting a register towards right side by one time, or load the register from the memory, or store the register from the memory to register, as a register to memory, and then clear a register. This register value will be make 0 and increment the register. Simple value will be incremented by 1, or set all the registers with 1. So these are some basic operations. It is the operation done on the registers only. So it is also called an elementary operation performed during one clock cycle. So just in one clock cycle, the values processed within the register can also be considered as a micro operation. Uh, uh, so next one, how these micro instructions can be performed. It is correlated with A is simply represented with some small diagram. A register is connected with the bus, internal bus, and also A is connected to the internal bus input and output. These registers are multiple registers are there. It will be selected from the multiple registers. But here we have considered only one register is there attached with the A. This register set is connected. So register 1 is connected to first input, another register 2 is connected to second. It will perform some operation and it will generate the output and it will store this in one of the registers. So any operation like shift, add, load, clear, increment, add, these are all the basic instructions used to perform huge, bigger instructions. So let's see how these micro instructions are organized in a computer. So we know the set of registers and functions for a given process. Micro operation set means the set of micro operations allowed by the computer. So it has some set of micro instructions that can be used. So any processor means it is having some it can do some 10 micro operations, it can do some 15 micro operations. That set must we should know. And also how many registers are available in the register, available in the processor, that also to be known. And the control signals that initiate the sequence of the micro operations has to be understood to learn about the micro operations. Now, register transfer level. So, register transfer language is just the any system or any processor how the transfer of instructions will be taken place within the register is indicated with the register transfer level. So in different ways of transferring the values or the data between the registers, that is the register transfer level. So this is focusing based on the system registers available and data transformations between the registers and the data transformation for any other purpose. What is register transfer language means? It is some symbolic representation of the transfer of data between the registers. So instead of specifying in terms of languages, move like so for example move A comma B. So it is not a register transfer language. It is an assembly level language where some kind of mnemonics, a code is used to specify the operation. But here there is no codes are used, just symbols are used. So for example, R1 has to be transferred to R2. So R1 arrow mark is specified towards R2. That indicates the transfer of data from R1 to R2. So it is a symbolic representation of transferring the data or performing operations, any other operations also. So to function the computer, as we have said, the register transfer language can be used to specify the basic micro operations. The basic micro operations can be easily represented with simple symbols, symbolic language. So now let us see the registers part. First, once if you know the registers, what are the basic kind of registers available in any processor? Even if you take a single processor computer also, what are the basic registers that are available in the processor? And then how these registers are used to specify any register transfer language, that is symbolic language to indicate the micro operations. So the most often registers are so memory registers and instruction register and then a program counter is basic requirement. So memory register and along with this one, it may require data register also, or data register. So memory address register, memory data register, and then an instruction register and program count. The memory address register holds the address of the memory location where the data has to be stored or the data has to be retrieved from. And instruction register is just to store the instructions only that are fetched from the memory. And program counter is just to keep track of the instructions that are executed by the processor one by one. So after executing the first instruction, next instruction is the address or the second, maybe second instruction is the next instruction address, or it may be 10th instruction address, maybe the next instruction address. So that can be kept track by the program code. And program data register is memory data register is the data within that memory location, the value stored in the memory location will be transferred to memory data register. So address and data are the two basic representation of any memory. And it may have some additional registers. So it may be having some accumulator register. Basic microprocessor mostly contains one accumulator along with MER and MDR and PC and instruction register. So if the processor architecture is improved, so it has so many features, and to fulfill the features, it may need some set of registers, additional set of registers for the purpose of general data operations or any specific purpose of operation. So that can be depends on the processor version. So next, so if you see the designation of registers, how the registers are represented. So in the micro operation or register transfer level, register transfer language. So register is represented with capital R, and if we have more number of registers, we can represent with R1, R2, R3, and so on. And the bits stored in the registers are represented with its index. So the bit index is represented with numbering from the right side to left side. So 0th bit is at the rightmost, and MSB bit is its most significant bit is at the leftmost side. So you can see here. So 0 to 15, this can be 16-bit register. So it is indicated with 0 at the rightmost and 15 at the leftmost. It indicates it's a 16-bit register. Or we can indicate the individual bits also on the top of the register. 0 to 15 we can write completely. Or some registers are byte access. So byte accessible means it is a 16-bit register, but store or we can use half of the register to perform any operations. That is byte accessible register. So this is this PC is, let it be some example, PC register is 16-bit, but it can be accessed even PC high and PC low also. We can just store only 8-bit instead of 16-bit in either lower part or upper part of this register. This is some symbolic representation of any register. So portion of bits can be represented, bits can be represented, complete word can be represented in a register. So next, register transfer. So we have seen what is register transfer language, and what is register, how it is represented, and what is micro operation, just we have discussed. Now, so how this register transfer is basically represented. So symbolically, instead of mentioning in word or any code, here as an arrow mark is indicated from source to destination. So in most of the this transfer language, the source is represented at the right side, the destination is represented at the left side. So R1, the arrow mark is towards the destination from right to left. That means R2 is at the end point. So R1 data is moved to R2. So R2, when a data is moved from R1 register to R2, it indicates R2 data will be replaced by the data present in the R1. But whatever the data present in R1 will not be erased. Just like copy the data from the R1 register and just paste in the R2, or we can replace the value present in the R2. R2 content will be changed, but R1 content will never be changed. So this can be done in one class. So just we can see how this can be done in one class cycle by using this architecture. So here, for example, this indicates the data register transfer such as R3, R5 to R3. So R5 value present in the R5, the value present in R5 will be loaded into R3. It can be done in one clock cycle, means all the data will at a time will be stored into R3. This is called parallel load operation. So this parallel load operation can also be a control function. It is also associated with the control function. So the control function means whenever some condition satisfies. So for suppose some is indicated with some if the result is 0, or if the result is negative, or if some other register is negative. If R3 is equal to 0, then we want to transfer the data from R1 to R2. This is the condition. So it is indicated in the register transfer language as like this: P colon R2 R1 to R2. So P colon that indicates P is the condition. Colon is used to represent it is a conditional control transfer. It is a conditional control transfer. The condition means based on the condition, the transfer will take place. The condition is true, then only the transfer will take place. If the condition is false, then it won't transfer the data from R1 to R2. So this is called a control. So conditional, and based on the condition, the transfer will be controlled. Right? So this is one kind of micro operation in the registers that can be represented with some. So this is language point of view. So P colon R1 is transferred to B. But what happens actually within the architecture? So there is a simple control logic will be there, control circuit. That control circuit output signal, a control signal is connected to the destination register. Destination register is the one where we want to give the result from any source. So here R1 is connected to R2, but the control pin is connected to R2 only, not R1. So R1 can transfer at any time, but R2 has to receive based on the condition. So if load is 1, the data from R1 will be stored into R2. And the clock is transferred commonly connected to both. So when clock is high, so both will be enabled, and it will be transfer will be enabled only when load is. So this is a timing diagram. So the clock pulse t to t plus 1, the load is high, but remaining the load is 0. So when load becomes 1, then data present in R1 will be completely transferred to. So it can be at any edge, positive edge also the load can be high, or negative edge also the load can be. So if it is load becomes high at this edge, at this negative edge, so then it is called negative edge triggered flip-flop. So these registers are a combination of flip-flops. All these flip-flops are connected to clock. So when clock is high, then all the flip-flops will be enabled to receive the data. But based on the control, it will receive. And so next, before going to discuss about the micro operations, so let us see some basic micro operation and how it will be represented with the symbolic representation. So for bus transfer and relay transfer. So we are going to discuss this logical arithmetic and shift micro operations. We should know how the transfer takes place in terms of. So this is the control transfer from one register to another register with the help of a control circuit. So now let's see the simultaneous operations. If such a kind of transfer has to be performed parallelly between two different transfers, register transfers. So when control logic is high or true, when P is true, then the data has to be transferred from IR register to MR and also simultaneously R5 to R3. So this can be done simultaneously and parallelly because there is no dependency between these two transfers. IR, MR is two different set of registers. R3, M5 are two different set of registers. So there is no dependency between these two transfers, so it can be done parallelly. So next, so these are all some basic SIM register transfers and their symbols. So generally, the registers are represented with letters and in combination with numerals also. MER just purely letters, R2, but it is combination of register names using letters and its numbering is represented with some numerals. And to denote register bits, the bits are represented within the parentheses. Parenthesis symbol is to indicate the R2 contains, the R2 is index 0 to 7. R2 of L means the lower byte of R2 register. 0 to 7 can be represented as R2, R2 of L. Next, so the transfer is represented with arrows and colon is used to indicate the control function, P colon, and comma is used to indicate the multiple transfers or multiple instructions. And now, so this register we have seen what is the register transfer language and how it is represented. Now, how these registers are connected to the external devices like memory, so or any other device, or within the within the processor, how the register is connected to the some ALU, or it can be connected to some other register. So if you want to connect, we need generally three kind of buses. To connect with the memory, we need address bus, data bus, and control bus. So address bus is to point out where the location where memory is to be accessed, and data bus is just to get the data from the memory or store the data onto the memory location. The data will be transferred through data bus. And control bus, so whenever the control is true, then only the transfer has to be enabled. So the transfer is controlled and this control signals are transferred through the control bus. Now, if you want to connect these control lines directly to perform parallel simultaneously, connect multiple lines for every register. So this is it is not possible. We have n registers. N registers must have n control bus and n data bus has to be connected parallelly. So it needs so many interconnection approaches. So it becomes a complex task. So instead, it can be organized based on a control circuit, a centralized set of circuit for data transfer. So that is called a bus, but it is controlled by using some control signals. So it's a we can say three-stage bus like kind of thing. It's just not only transferring the data; it can be controlled. Not to transfer is decided by some control signal. So this bus is common bus. So any register can be placed the data onto the bus. It does not have separate buses for every register. The common bus will be provided, but the transfer of data between the registers will be based on the control circuit. Now, let's see the transfer of data between um, the registers or the bus. It is called the bus to bus transfer. From register to bus it is, and then bus to register transfer. So it is completely from bus to bus transfer. So assume it has four registers: register A, register B, register C, and register D. And this data has to be connected. The data has to be transferred between the registers or has to be transferred to some memory. So how this data will be transferred from source to destination? So directly it will not be transferred from source register to destination. For example, A to B, if we want to transfer, directly it cannot go A to B. There is no direct connection. The common bus is, all the registers are connected to the common bus, and the common bus is connected in both the directions to the registers. Here, how this data will be transferred from register to common bus. So all the bits of the registers are connected to the particular bits of the multiplex. So we want to select, here it is a control base. We said it's a control based. So instead of using a particular control base, we can use multiplexers also. So to send the first bit in all the registers, we will use one multiplexer. So all the first bits of the four registers are connected to first multiplexer. Here it is four inputs, four registers are there. So first bit from all the four registers form 4 bits. So it is connected to 4 by 1 bits. So if you want to transfer A register, only first bit of A register will be transferred from first ones. Similarly, second bit of all the registers are connected to second ones in an order. So first register bit is connected to first line, second register bit is connected to second line. Like that, with some order it will be connected to the ones. So there is a select line after register select. For example, we are selecting register A to place the data onto the bus. Then 0 will be selected. So this, to select among these registers, we are using 2-bit control signal. When it is 0, it indicates register A. When it is 0, 1, it indicates register B. When it is 1, 0, it indicates register C. When it is 1, 1, it indicates register B. So when these control signals are commonly connected to all the registers, when it is 0, 0, these control signals are connected to mux select line. When it is 0, 0, all the mux will enable first input to flow to output. So first input is nothing but what? First bit of the register A. So first bit from the first register, second bit from the of the register A get from the mux 2, and third bit of register A is connected to first bit of the third mux. Similarly, fourth bit of register is connected to first bit of mux 4. So when it is 0, 0, all the first bits, all the first input of the muxes will be transferred. So all the first inputs are nothing but A bit registers. All the second bits are nothing but B bit registers. All the third bits are nothing but C bit registers. All the fourth bits are nothing but fourth bit of the mux. So when it is 0, 0, all the muxes will give the 4 bits. The 4 bits are nothing but coming from. So it is connected to the bus lines. So like this. Now, from bus to destination register. So yes, the bus is having 4 bits. Now we want to transfer to destination register. So we want to transfer to, let it be a register R2. Some R0 to R2 we want to transfer. Some R0 value is already placed on the bus. Now it is connected to all the registers actually. But the register has to load based on the condition. So the condition is one true means then that particular load signal will be enabled. So here we are using control or decoder logic that will generate only one control signal is high, remaining all are zeros. So decoder, so here I will select register, destination select. So there the source select is represented with mux select line, and here destinations register is represented with decoders. If it is 0 0, D naught will be 1, D naught is connected to 1. If it is 0 1, so D1 is output is 1, that is connected to register R1 loading. So at a time any one register is selected, so that register is represented as a destination. Now, so these control signals are connected to some three-stage buffers. These registers can be connected with not directly connected. It can be connected to like a tri-state buffer. So here, if the tri-state buffer is high, say the select line or some decoder output is 0, then this buffer will not be enabled. So that bit will not be transferred to the output. So the bus is almost high impedance state. It is open circuit. So if it is 1, then only it is high. So at a time, any 1 is high, that is any one register is selected. So a particular bit of one register. So for if it is having 4 bits, so 4 such circuits are required. And now we'll see in some RTL language, we'll go for the memory transfer. See some micro. So yes. So now we have seen architecture level how the data will be transferred from register to bus and bus to register. So this RTL in register transfer language, this micro operation is also a micro operation. It is represented in RTL as R1 to towards bus and bus to R represented in terms of like register language. Now, so the register to register transfer is discussed. Now, let us see the memory to register transfer and register to memory transfer, and then we'll go for the micro operation. So, there are two types of memories we can see. So, random access memory and read-only memory. So, random access memory is uh, any memory location can be pointed out at any time. So there it is not like sequential. We can point out 0th address and we can take the data, or we can point out some 100th address. We can access the data. So this memory is represented like generally in data bits multiplied by number of locations. So the 2 power k words. So that it contains k address lines means 2 power k address locations it can generate. So 2 power k locations, and each location contains, let it be the word length 8 bit means 2 power k by 8 is the representation of the memory. So this memory, apart from this address lines, it has data lines. These data lines are like a bidirectional line. So data input or data output. Only represented generally in one time only is both the directions. And so after pointing the location, it can access the data. So the data can be stored into the memory, or the data can be retrieved from the memory. So that is specified by the two operations called read and write control signal. It is read. The processor reads the data from the memory. So memory does not read. Only the processor is the center or control. so processor reads the data. So the data is outside from the memory towards the outside, the output of the memory. And write input means processor writes the data into the memory, so it is in data in the indication of RAM. So now it is memory transfer. As we have indicated, the memory transfer is also done by using this bus to memory register to memory. So a memory register is the source, and from memory register it has to find out the memory address register, it has to find out the memory, and it has to data set the, read the data, write the data into or from the memory. So data out and data in. So when AR, when this read or write signal, at a time any one input is enabled, either read is enabled or write is enabled. This is read is enabled, then data in will be enabled. This direction will be controlled by using this read. When it is controlled, then this is ready and AR data will be placed onto the. So the symbolical representation of memory read operation is so this is M of MER. M within the square bracket the register M of MER. That means the value present in MER is content of MER. This can be read as content of MER. So content of MER means the value present in MER will be used as the address for the memory. So if MER is equal to 10, let us assume MER is equal to 10, then it will go to address register is 10. That address is connected to 10th location. In the 10th location, what it has to do, the data present in the 10th location will be transferred to R1. That is content of MER means, so memory content of MER. Memory content of MER is address. In that address, the content stored in MER is data. That data will be transferred to R1. Or R1 can be written into the MER. At the time, this the position has to be swapped. So as we see, the contents of the space field will be put into the memory output data lines. This gets sent over the bus to be loaded into the register. So that process we have seen, bus to register, register to bus operation we have seen. So similarly, this memory rate R1 to M. So these are all some summary of micro operations. What we have seen, that's transfer between A register and B register. Transfer some content of the DR and B, some portion of DR and DR. So some constant also we can transfer, or bus to register, register to bus, or address register, data register. That can be represented AR, DR, M of register, content of register. And memory to data register to memory also. Now let us see the micro operations. What these are all the basic instructions and what are all the basic operations that can be performed with. So register transfer micro operation. As we have discussed so far, what is the transfer of data between register to register or register to memory or so. Now we see the operations performed within the processor, not with the register. Register once get the data into the processor. The processor will do operations using micro. Yeah. So what are those operations done in ALU? We'll see this. Right. So the four types of micro operations. Let us see this. One is register transfer micro operations. Second one is arithmetic micro operations. Third one is logic micro operations and shift micro. So the basic arithmetic micro operations are addition, subtraction, increment, and decrement. So addition micro operations can be additionally can support add with carry, subtract with borrow, and addition can without performing addition just perform transfer and load, etc. Just add with zero, you can get it. So these are the summary of the arithmetic operations in register transfer language. So R1 plus R2, it is symbolically represented. Instead of saying add R1 from R2, you can say R1 plus R2 is arrow mark with this. So equal to generally most indicate. Equal to means so how the transfer is taken place cannot be mentioned specifically. In a high level language, it can be mentioned. Right? Equal to generally the R1 plus R2 will be equal to R2. But here more specifically we want to mention which is source and which is destination. So the arrow mark points from source to destination. So similarly R1 minus R2, the content of R1 is transferred to R2. So similarly R2 minus R1 can perform, or R1 minus R2 can perform. That will be transferred to R3 and R2 complement. The complement of R2 is stored again in R2. So and R2 bar plus 1 means 2's complement of it. Negate, you can say negate operation. Negate is the NG, the instruction used in the assembly language. So R1 plus R2 dash minus 1. So but generally the R1 minus R2 can be performed using 2's complement addition. R1 plus R2 dash plus 1. And increment R1 plus R1. Decrement R1 minus R2. R1 minus 1. So these are all the architectures within the processor. Some basic architectures, binary addition, adder or subtractor, and binary incremental addition. So addition means just we'll use bitwise addition, full adder. For every bit pair we'll use one full adder. It will take input carry from the previous bit addition, and it will pass the sum to the result, and it will pass the carry output to the next bit addition, next MSB bit side. Generally, it will flow from LSB to MSB. So the same circuit can be used as subtractor also. This is second bit is connected to XOR. Every second bit is connected to XOR gate, and another input of this XOR gate is connected to mode bit. Mode is 0, XOR bit, all the one of the input is XOR bit is 0. 0 XOR the input is input only. So when M is 0, it will be used as addition. So A0 is added with B0. So XOR will just pass B0 only. If M is equal to 1 means XOR 1 means negation of the bit. Any bit XOR with 1 means negation of bit. So the XOR gate will pass B0 negation. B0 for negation means it is complement, not negation, it is complement. B0 complement transfer. The same one is connected to here because A plus B bar plus 1 is 2's complement addition. That is nothing but subtraction. So this one is connected as carry input to the first tuple and it is connected to any chain. Or if this is adder or subtract, same circuit can be used. And another two operations are binary increment and decrement. So increment operation, just this is connected with one. First input is half adder will add. One input is added with plus 1. So we use just simple half adder can be used instead of full adder. So first bit is connected to LS bit is connected to one input of half adder, another input is constant 1. So if it is added, it will generate some S0 and carry will be chained. So there are nowadays there are so many architectures that can perform efficiently than this chain based operation. Similarly, subtractor means here it is A minus B means A plus minus 1 2's complement of minus 1. Okay, so this is completely arithmetic circuit. So we have done four circuits. We have 4 circuits to perform these operations, and these circuits will be enabled based on the instruction. Here, this arithmetic circuit can perform almost 8 operations it can perform. So the 8 operations is performed based on the in select lines. So the select lines is connected to mux and two inputs are A, B are connected. So based on the select line, the second operand will be select. So first operand is always A. So first full adder, all the full adders are connected to first operand input. The second operand is B is connected based on the selection input. If selection input is 0, 0, then add with B. So it will just pass B value. So multiplexer connected four inputs, four by 1 mux. The first input is B naught, the second operand bit as it, and the second bit is 0th bit, and first bit is B naught bar, and second bit is just it is 0, and fourth bit is 1. First one is B naught bar, 0 and 1. So if it is select line is 0, 0, all B naught, B1, B2, B3, B4 will be transferred to the full adder. So it is nothing. First operand is A, second operand is B. So the output is A plus B. The second operand is B bar. Then it is A plus B bar. So A plus B bar is nothing but subtract with borrow. So subtraction means A plus B bar plus 1. Where plus 1, if we remove, then it is A plus B bar means subtract with borrow. We just subtract minus 1 also. Plus 1 minus 1 get cancelled. Okay. So similarly, when it is 0, 1, 0, 0, 0, 1, 1, 0. No, 1, 0 means all the second bit is 0. So A plus B. A plus B is 0. A plus 0 is equal to A. So this is just a transfer. If it is 1, then the last bit is 1 means so it is all the ones will be transferred now. All the ones means it is 2's complement of it. So when it is 0, 1, 0. So when it is 1, 1 B naught bar, and carry depends on carry also. Carry is 0, then it is subtract with bar. If carry is 1, it is only subtract. A plus B bar plus 1 means it is subtract. And if it is 1, 0, transfer. If it is 1, 1, 1, select line is 1, 1, it is subtraction. If carry, based on the carry, it will decide whether it is subtraction or increment. So for all ones means, so carry is also 1, and it is 1, 1 means B bar. So it will transfer all ones and plus 1. All ones plus 1 means it is nothing but 0 only. So last one will be eliminated. So 0. So 0 plus A means again it is a transfer. So it can perform transfer input, or it can increment, or decrement, or it can perform subtraction with or addition with carry. So everything is based on the control system only. So now logic micro operation. In logic micro operations, we will do some bitwise operations. So here it can perform almost some 16 operations, 16 logical operations, that is AND operations, XOR, complement operations, that perform bitwise operations. So what are all the logic micro operations that can be performed? So it has 16 operations can be performed. So let us see that 16 micro operations here, and just we have to understand the instruction level transfer. Right, so these are some set of micro operations. So here it is 0, 0, 0, 0. So which indicates 4 variable function. So it will be clear, F function will be clear, and if it is 0, 0, 0, 1 AND operation, and X Y bar operation is 0, 0, 1, 0. It will perform. So what is this code actually indicates? So AB are inputs, but for different logic it needs a code to perform. The code is some kind of code. So it can perform clear and transfer and A bar and B bar are A bar and B bar are A and B bar. Exclusive all operations, transfer operations. These are all some basic bitwise operations. So this can be, if it is 16-bit means 16 micro operations means we need 16 by 1 max. So if it is for the understanding, just we have taken only 4 micro operations using 4:1 max. So just micro operations can be performed by using logical operations. Logic gates, necessary logic gates to perform the operation that can be connected to mux to select one of the operations. That's all. So these are some kind of logical operations, selective set. So here it is masking is concept is there. So if you want to perform any one operation on a particular bit, you want to do some kind of uh, second operand to be fixed. So if you want to, for example, selective set operation, you want to set a particular bit in a register. You want to set a particular bit in it. So for example, 1100. So 1, second bit is 1. So third bit is 0, fourth bit is 0. So here it is left from left side LSB 0, LSB first LSB are 0, 0. We want to set the second one. So you want to set the second one, you want to perform addition of 1 at this particular position, 0, 0, 1, 0, 1 grab. So then it will be like that particular bit will be set. Now selective complement. If you want to complement it, we want to do XOR operation. So if any bit is wants to do, so just we will do XOR operation. So same bit XOR is 0. Opposite bit XOR is 1. So if you want to be sent as it is means we will XOR with 0. If it is 1 wants to be complemented means we will XOR with 1. In selective clear also said we will just perform AND operation. If you do AND operation with 0, the particular will be 0. If it is 1, it will be multiplied with 1. So next one is shift micro operations. So shift micro operations like it is a serial shift operations. At the time it will perform one shift in one clock cycle. If you want to perform more than one shift, we can perform. We can indicate the count number of times this will be repeated. So right shift means generally at the MS bit will include 0 and bits will be transferred. So bit will be transferred and at the MS bit it will. For example, this is 8 bit. So already 1111 so 101 some pattern is there. If it is right shift, just it will shift the right bit position to towards so the leftmost bits by one position towards right. All the bits will be moved by one bit position. The LSB will be discarded and MSB will be new position will be created. At that time we will add 0. Similarly, left shift means at LSB will be shifted to next towards next MSB bit, and all the it will be reach up to MSB. If MSB is discarded, so the leftmost bit will be discarded, and but at the LSB bit will add 0. So similarly, instead of logical shift, there is the arithmetic shift also. The MSB bit has to be kept as it is. We'll copy MSB bit as it is and will perform right shift. Okay. So that is MSB bit generally indicates the sign of the data. So we don't want to change the sign of data by performing shift operation. So if it is positive, we'll copy the 0 as it is and we'll write it. This negative MSB is 1, so we'll keep MSB 1 and we'll do right shift operation. And in left shift it won't happen. And similarly, circle right circle shift operation, or we can say rotate operation. So rotate right or circular right angle shift. Circular right angle. Or rotate right can also. So what is rotate right operation means? So always rotate right means we'll start with the rightmost bit. The rightmost bit will be transferred to leftmost, and then it will be right shifted. So this data will be right shifted, and the last bit will be come to the new position. One bit will generally in the shifting, one bit will be discarded, and one new bit will be added. Instead of discarding and adding new bit, so the discarded bit will be come back and stored in the new bit position. That is the rotation. Similarly, left circular shift means left